is Mitsumatsu. Yosh will tell us about Helicity in differential topology.
Thank you. Thank you very much for the introduction. And I thank the organizer to give me this opportunity to give a talk here in this conference. And I have to confess that I'm really pure math people are kind of differential topology or differential geometry. So today I'm going to talk about helicity and how it is used in differential topology. But I would like to present one problem which is between topology or foliation theory and fluid dynamics. And I would like to give some answer to that question using the helicity. But the way of using helicity is quite different from those in the most talks in this conference. So you will see. And because I'm a topologist and then maybe a geometer also, so my our first interest is to understand the manifold, the space itself, or sometimes the geometric structure, some geometric structures on the space. And usually the geometric object is not linear, and so it's a bit difficult. So what we do is to set up some, for example, some vector bundle, and look at all the cross sections. So it's a linear space, even though it is infinite dimensional. The space of the sections already it's infinite dimensional, but still it's linear. So we can deduce some linear data. So that's the basic idea to bring the global analysis into geometric problem. So it's really, I think it's a natural idea to bring fluid mechanics into analyze the manifold. So if you take a manifold and you put the water on the manifold and how it look at how it flows and analyze it, and I would like to deduce some geometric information from the fluid dynamics. But very unfortunately, the analytical foundation of fluid mechanics is already very difficult. For example, the global existence or uniqueness of the solutions, that's a really difficult problem. So this idea might turn difficult geometric problem into much harder problems. So it might be not so good. But sometimes it looks really interesting and still tempting. So for example, I only consider about the incompressible flows, but and I've been for a long time working on foliation theory. So I will present you some problem like this. So if you take a torus, two-dimensional torus, I draw like this. And if you take a very simple foliation, one-dimensional foliation, and if you put water here and look how it flows, but there is one constraint because, namely, the flow should go along the leaves. Okay, so the fluid particle can move only in the direction of leaves. Okay, then in this case, before starting the fluid mechanics, we have to know the space of incompressible flows. So if we have a manifold M and a foliation F, then I will write the space of vector fields, which is tangent to the foliation. And if I put subscript D here, that means divergence free. Okay. So in this case, two-dimensional torus, and if you have a very simple foliation like this space is very well understood. It's easy. So because if we take xy coordinate like this, then all the incompressible flow which is tangent to these leaves are of this form. So in the x direction, the coefficient is constant. The coefficient can vary in y direction. Only that. So in this case, this is this very simple, let me call F0. This is, no. This is a smooth function. This is exactly the same as the smooth function on the circle, y circle. But if you take irrational foliation, then if you think about it a little bit, you will see that this space T2. So the angle is 1 and alpha. So if alpha is irrational, so let me call the foliation f of alpha. This is R. So the constant vector field is ddx alpha times ddy, and it's constant times. That's all. It's quite easy to see. Then the next question is that if you draw the same thing, same picture, but if you put some different area forms, well, if you change the volume of the space itself, you don't change the foliation, but you change the. So if you have less area element around here, and I think it is the same thing to say that draw the same picture and don't changing the connection, but you push a little bit line like this. So because this here on the transverse direction distance is a little bit distorted. Okay. In this case, what happens with irrational foliation? And then it depends on alpha. So in this case, if the alpha is of Diophantine, then this one is with the volume form. This is very diffeomorphically equivalent to the original one. So this is very important point. And so this is again this flows. But if alpha is not Diophantine, namely the, a kind of Liouville irrational number, in this case, I don't know. There are two possibilities. Still, it can flow, or it doesn't flow at all. It depends on how you perturb it. And so already in two-dimensional case, the question is not so simple, but not so difficult. So I try to think about the same problem on the three manifold with co-dimension one foliation. Diophantine is badly approximable irrational numbers. So for example, E or pi or algebraic numbers, they are all Diophantine. And most of irrational numbers are Diophantine. from some point, yes.
Are all volume forms diffeomorphic? So there's always a diffeomorphism that sends one volume form to the other.
Well, yeah, in the sense of volume, area form. So there is a diffeomorphism from here to there, which preserves the volume, area.
Right. Oh, I see. But it may not.
That's why they are quite equivalent. So you have to do some sort of some functionalization. Yeah. Yes.
Without necessarily going to the 3D, what happens on other surfaces than the torus in 2 dimensions? Is that known? The classification?
Yeah. Because if you take a non-singular foliation, then others are something like this. And I should mention because, for example, if you have a two closed leaves, and in between the flow foliation goes like this. In this case, it doesn't flow at all. you can see that because how you can push into the yeah. That's why it doesn't flow. So in this case, we can show that no incompressible flows. And in other cases, it's easy to see. So,
Sorry,
yes?
I'm sorry. Review number.
A review number, the other case. Not the part time. I'm sorry. So the review rational numbers are well approximable by rationals. Don't ask me too much anymore. So I want to go slightly further. This is only a warming up. Okay. So I yeah. Okay. So I'm going to think about three-dimensional case, but I have to use a helicity. I will make a heavy use of helicity. So maybe I write this. So even on a closed free manifold, we can formulate the helicity. And the helicity in fluid dynamics, usually first we take a velocity field u, and then take its curl, and quite often it is written in omega, and take its interior inner product, and then integrate it on the space. But in my case, the space is manifold, and put dvo. And this is called the helicity of U. And maybe this part or this part, with volume or without volume, maybe I will call this one small head of U. But in the previous talk, it appeared also that if you look at omega, and the helicity of this quantity is interpreted as the self-intersection of this omega. That is a really important point. So I will formulate how it works on free manifold. So here is the space of vector fields on the manifold, and inside we have a divergence-free vector fields, and inside so the manifold has if the manifold has non-trivial topology, then it has first cohomology, homology, cohomology, and if you take, here is the first point, if you fix a volume form on the free manifold, and if you plug the vector field in here, then the vector field corresponds to two forms on the manifold. So this denotes the two forms on the manifold, and here is a closed two form on the manifold. These two correspond to each other exactly. And then, if the manifold has non-trivial topology, then space of exact forms and the closed forms are slightly different. The difference is the second cohomology. And so here it corresponds to some vector fields, which I call homologically trivial. So the subscript means homologically trivial. And this we use the volume. That with these correspondence, we use the volume and the interior product. But if you fix a Riemannian metric, if you want to do really fluid mechanics, we need a Riemannian metric. And the metric, if you take a metric dual, then also this corresponds to a one forms. And in that sense, this corresponds to not a closed, but a so-called co-closed. So co-closed one forms. Yeah. And here, co-exact one forms. And if you start from here, if you take, maybe I do a different. If you start from here, if you take U here, You can take also take from here. Then you take U, and then what you are doing to compute the helicity. First, take the metric dual. So here is something corresponding. This is alpha, and then you differentiate it. then it comes all of a sudden here d alpha. It's a closed form, and then here corresponds some different vector field. So that is omega. Okay. And in fact, in this terminology, so you don't have to take U and the curl of omega. And in fact, if you take two vector fields from here, x and y, if x corresponds to d alpha and y corresponds to d beta, so first, to compute helicity from omega, we have to compute the curl inverse to get U. That is nothing but taking the inverse of this exterior differential. But we have a lot of choice, but it doesn't matter for the integral value, integral invariant. For this function, as a function, it matters, but as a value of integration, it doesn't matter. And in fact, we can define a linking, asymptotic linking. This is the asymptotic linking of the vector field x and y. And this is nothing but alpha, the integral of alpha wedge d alpha, alpha wedge d beta. Simply that. So from this scheme, you can see that the helicity is, if this is translated into this way in terms of differential forms, it is a symmetric bilinear form on this space or on this space. And it has a really good properties, symmetric, bilinear, non-degenerate. And even for very strong sense, it's adjoint invariant. So it's something like a Killing form on symmetric, simple or semi-simple Lie algebra. So it has a really nice property, but so far we couldn't. So this is found by Arnold and proposed since long ago, but we couldn't use, we couldn't have used that adjoint invariant property. Maybe that's a future program. Okay, this is the way to. So we have to think about in this way. So it's a non-degenerate two form, but already the time is coming. So the point is that so to do fluid mechanics, we need a metric structure at least. But to formulate the helicity in terms of asymptotic linking, we need only a volume. And if you translate it in terms of differential forms, you even don't need the volume. So you don't need anything, only the orientation. In terms of differential forms, it is defined without volume. But anyway, if you have a codimension 1 foliation, then what I'm going to take is the following space inside the space of exact two forms. Here omega is the defining one form for the foliation, and f is a smooth function. The tangent plane of the foliation is the kernel of, and here omega, because of the Frobenius integral condition, omega, d of omega is omega with something, eta. Usually we call it eta. And so this is another description that take all one forms which vanishes on leaves and take its exterior differential. then you get a very large subspace in the space of exact two phones. And what is interesting is that this subspace, linear subspace, is null subspace. If you start compute, then you will see in 1 minute. But anyway, from this integrability condition implies that this is a null subspace with respect to that linking pairing. So how I use the helicity as a linking pairing is not look at the single flow and computing its helicity, but I will look at all the flows and all the linking pairings. And so from that point of view, if you have a foliation, then you have a null subspace. Then because of I should stop. Let me use a kind of high-tech missile. So this space is this space is really interesting, still interesting, and this space coincides with what we are looking for. MF. This is very easy observation, but what is interesting is that so because this null subspace, this is a null subspace, so it is contained in its orthogonal complement with respect to this linking pairing. So we can take this quotient, and naturally the original symmetric bilinear form is in this here. And we have a surjection from the so-called Fourier cohomology. And this is really difficult stuff to compute, but for certain foliation we can compute. And usually this is of infinite dimension, but for very specific three-dimensional foliations, we know that this is in some cases. This is finite dimension, R. And that implies, so I will show what is a foliation. One foliation is that if you take a torus and let the matrix, for example, 2, 1, 1, 1, it's an integral matrix and with trace greater than 2, so meaning this has two eigendirection, which is one is expanding and the other one is contracting. And choose one of them, maybe taking one expanding. And then you take a suspension with this monodromy. So you get a three manifold, which fibers of a circle, each fiber is a torus, and if you come back, then it is twisted like this, right? This matrix. But if you take this eigendirection, the eigendirection is preserved by this monodromy. Then these all parallel lines come back to the same parallel line, the other line, but one of them. So this gives you a codimensional foliation. For this foliation, we can show this one. The heart is something really close to this Diophantine story. And in this case, we have this one, and we know that the space is this. This space is, this space is R plus. This R is nothing but this flow, this suspension flow. This is volume preserving flow, and the other part comes from here, because this is the space that we want to know, and taking the quotient, we know this one. And for this one, this is really easy, because the foliation is, even with volume form, if you look at very locally, it's really standard. So you can produce a very local flow which volume preserves. So this part is exactly what is generated by those local stuffs. And only one, you have to add only one flow, which is generated from. So a priori, it's not so trivial that if the foliation has some non-trivial holonomy. And in the case of two-dimensional case, if you have these picture, it doesn't flow in this way. But in higher dimensional case, if it is going to closer, the leaves are coming closer, but you have some room to escape in other direction. But in global, it is not at all trivial that it really flows in that way. But the Fourier cohomology provides you some to solve that point. And this is the way to use Helicity. Thank you very much.
Before questions, please don't evacuate the copies. We take group photos after questions. So please feel free to give questions.
So usually, as a physicist, we don't pay too much attention to such a difference between, say, omega and d alpha or something like that. And what situation do you say that we have to be careful?
You mean physical sense?
Yeah, these particular.
I'm sorry, that I don't know, because codimension 1 foliation on three-manifold is not so natural in physics. So this is a kind of mathematical question, puzzle kind of mathematical quiz simply from a geometric curiosity, I think. But some places you have, but I'm not sure.
So can you get some information, what kind of gauge we have to be careful about?
That's a very good question, because as I told you, so for fluid mechanics, you need a Riemannian metric, otherwise it's meaningless. But the title of this conference is Topological Fluid Dynamics. It sounds that we can forget about Riemannian metric. But at least, as I worked, at least we need a volume. But in the final stage, I even forget about the volume. If I work on differential forms, for a certain moment, I can forget about the volume. But at least we have to come back to the volume stage. And for those particular foliations, the same thing happens again in this example. And if you put any volume, they are all equivalent. This is a little bit magical situation only in this foliation. So at least you can come back to the volume stage. And then, next you put Riemannian metric, then you can start fluid mechanics. So that's the next step to do. So we are ready to do a bit on that foliation.
I propose to continue discussion after photo and then continue discussion in coffee time. Thank you very much.